some doubts that you have raised, students have raised. Suraj has not joined. Suraj, he has raised 4 5 doubts, and Anvesha had requested for one freeze formula. So these two we'll discuss in the past lecture. Second lecture, I will tell you some examples of how to prepare, basically preparing for the end sem examination. So that will be second lecture. How you will divide your course, that we have discussed, which parts are important from end sem point of view. That is what we are going to discuss in the second lecture. Give me a minute, let me take some water and we'll start answering these doubts. And if you have any other doubts, please feel free to ask me. I'll be happy. We'll discuss. It's not a question answer session. We are going to discuss. बेटे ऑन कर दें. So let me start with questions of Suraj. The first question he had asked me in email. I have not received any doubts from anybody in the last week. Only Suraj has asked me before that. Last week I have not received anything. The question that he asked is why the region close to antenna, that is near field, is dominated by magnetic fields and far fields which are dominated by electric fields. Which means I feel he is trying to know, or this question is about which part of the electric field or electromagnetic field that is radiated is dominant in the near field region, and which part is dominant in the far field region, and why so. Now to know this, know the answer, the question is not correct in one say. In a sense the question is not correct, but to know the answer, let us go back to the first 4 5 classes in which we discussed the basic antenna as an oscillating dipole or the Hertzian dipole or the Hertzian antenna, and any other antenna, the linear antennas that we discussed, they can be thought of as an array of Hertzian dipoles, right? And in this array of Hertzian dipoles, the distance between two conjugative elements is 0. In that case, you just integrate the Hertzian dipole results over the length of the linear antenna or any other antenna that you are doing. So any antenna can be decomposed to its basic form, or the basic building block of any antenna is Hertzian dipole. Similarly, if you take a loop antenna, it is again a Hertzian dipole, but it is in the magnetic sense. This is Hertzian dipole in electric sense, electric dipoles. That loop will be equivalent to a Hertzian dipole in magnetic sense. Now, when we analyze this, we saw that the field regions for Hertzian dipole has 3 components. One is ER, E theta and H phi. ER is the radial component, E theta and H phi are the transverse components. So ER is gives you the direction in which it is moving. It does not give us the radiated field or the field component, actual field that is being radiated, or the energy, the field which contains the energy, that is not in the ER. ER gives you in the direction how in which it is moving and what is the amount of energy in that direction that you find out from Poynting vector. So we are not interested in ER. Even if you are interested in ER, you can see that ER has two terms. One term is proportional to inversely proportional to r cube, other term is inversely proportional to r square. It has no inversely proportional to r term. So here I am neglecting. Let us consider the other three terms. The E theta component, it has again three terms. The first term is, if you analyze the field equation, try to see that, you will see that the first term for the dipole can be divided into three different basic parts. For E theta, H phi and ER, there are three basic parts. Each of them will have at least two of them, and E theta has all the three parts. Now one of these parts is inverse distance term, proportional to r to the power minus 1, or inversely proportional to r. Inverse distance means inversely proportional to r. So 1 upon r. This term is called the radiation term, and it actually represents the energy flow away from the wire or away from the dipole. Now in this term is present both for the E field and H field, which means E theta and H phi. In both the cases this is present, and this is transverse to the direction of propagation. Therefore this is the radiated field. And therefore this is called the radiation term. So this is one term which is available in the far field. So the far field is containing both E and H, and you can also see that in case of a plane wave, we already know E is equal to eta times H, which means H is small compared to E. Right. Therefore, in the far field, the magnitude of E is larger compared to magnitude of H. E by H is equal to eta. Magnitude of E is larger compared to magnitude of H. By dividing E by E and H, you can find out that that is equal to eta. So E is eta times more than H, that we have already. Since this is a characteristics of plane wave, in the plane wave E is eta times greater than H. Therefore, the far field has both the components E and H, and E is larger than H in the far field. And then comes the next one, which is a inverse square distance term, which means proportional to 1 by r square. This is called the induction term because this is an induced field. This creates an induced field near the antenna. So this represents the energy around the antenna, which is detached from the antenna, energy around the antenna, and it is close to the antenna. So this energy goes out from the antenna, comes back to the antenna again. And so in the first quarter, in 1/4 of the cycle, complete cycle, this is the energy which is detached from the antenna but stored near the antenna. Next quarter it will come back to the antenna. Then next quarter it will go away from the antenna. Then it will come back to the antenna. This is again available for both E and H. Right? And both of them have equal dominance. It is not correct to say that This is called what is called the near field. It is not correct to say that H is dominant here. But please remember that here it is not a plane wave. Plane wave is in the radiation field or the far field. In the near field region, it is not a plane wave. So both of them are dominant, or both of them have equal dominance here, E and H. So their dominance is equal. It is, you cannot say that E upon H is equal to eta. In this region, E upon H is not equal to eta. You can find out what is E upon H. Just look for the coefficients of this 1 by r square in E theta and coefficient of 1 by r square in H phi. Take the ratio of E theta to H phi, find out what it is. So that is not a plane wave, that part is not a plane wave. So it is E is not dominant over H in the near field region. Other region, you can say that in one quarter it is inductive, then it goes back to the antenna next quarter it comes out as capacitive, then it goes back to the antenna as the capacitance goes down to 0. So capacitive inductive, so that is what is going to happen in this near field. Near field energy is for a quarter cycle it is capacitive, next quarter nothing, next quarter it is again inductive, so that continues. So since it is capacitive and inductive by equal amount, the dominance is equal in the near field. Then comes the last term, which is the variation of distance, cube of the distance, which is proportional to, so the variation of the field is proportional to 1 upon r cube, or 1 upon the distance cube. Now, this factor is not appearing in the H field term. H field term has variation of 1 upon r square and 1 upon r. Similarly, ER field has variation of 1 upon r square and 1 upon r cube. But the 1 upon r cube is only available for E fields. What is the reason for this? In the pre-college or in the pre-university classes, +2 science, if you have read, I expect that you have read the field due to a dipole, two opposite charges separated by a small distance. The electric field intensity due to this arrangement varies as 1 by r cube. So that is a small deduction that you must have seen in +2 when you have read electricity, static electric. So there you must have read this. So that means you require two charges, right? Now, when we are considering antenna, it is oscillation of two charges, two opposite charges separated by a small distance. Hertzian dipole is that. Since it's oscillation, therefore, we assume that at both the ends of this separating distance, there is charge accumulation, which is positive in one half cycle, negative in the other half cycle. So because of this charge accumulation at the ends of the element, you get this field, and this is because of the electric dipole. So only the E term only the E field has this term, and this is because of the charge accumulation. But this is not the near field. Near field is the other one, where you have 1 upon r square term that defines the near field. So I hope that you have understood what we discussed up to now. So this part is clear, I think. Then I'll come to the next question that Suraj asked. The next question is why the domination depends on distance in terms of wavelength of the antenna. By this, I think he means why we are dividing the far field and the near field range, or the near radiation field range, near field, near radiation field, and the far field range in terms of wavelength, not in terms of physical distance. The answer is very simple. For different frequencies, the same distance will have we can be uh, represented in terms of different electrical lengths. Therefore, usually instead of physical distance, we go for electrical distance. What is electrical distance? It is the physical distance divided by the wavelength. So that is standard. That becomes a standard. So this much of wavelength instead of this much kilometer, because if I say after 5 kilometers, the far field starts. Okay, so that will be in reference to a particular frequency. The frequency, once the frequency changes, it will not remain 5 kilometers. The far field will not remain at 5 kilometer. It may become 10 kilometer. It may become 2 kilometer. But if we say after 10 wavelengths or 2 lambda and the far field starts, always it will be after 2 lambda. Therefore, we always represent them in terms of lambda or wavelength. That is the domination or the field distinction, field demarcation is in terms of wavelength. I hope this is also clear. Uh-huh. Then the next question is, do the domination of magnetic and electric field is the reason for near field dependence on source and far field on propagating medium? Now, I could not understand this question properly, but I think the domination, there is no domination of magnetic or electric field. So the answer to that part is no. So do the domination of magnetic and electric field? That answer to that part is no for near field. Uh, uh, is the region for near field dependence on the source and far field on propagation medium. So near field depends only on the source. Saying that is not correct, incorrect. Is incorrect. But on the far field expression, that contains or that is determined by from electrical characteristics of the medium. If you look at the expression E theta and H phi terms, in those expressions you have uh, a component e to the power j k r divided by 4 pi r. So that part, take out that part. Then you have the current. Then you have uh, a term which is either in form of epsilon or mu or eta or c. Now all these c, epsilon, mu, these are characteristics of the medium. Therefore, the field actually depends on the electrical characteristics of the medium, right? Uh, uh, so the far field expression contains electrical characteristics of the medium. It depends on those characteristics. But the near field depends on charge accumulation of the antenna at the endpoints as well as on the medium surrounding the antenna. So there are two terms which are dominating the near field or which are determining the near field. So answer to this question I think is clear to you. Then there is the next question is, why the antenna and that radiates at lower frequency like few kilohertz are mounted close to the ground? And this question is continued in his next question. Is it due to its large size or other phenomenon that is responsible. Okay, now the answer to this is simple. Uh, One is the antenna. Why you are using a low frequency like kilohertz? Another, if you use low frequency as kilohertz or below kilohertz, then the antenna size becomes very large. Uh, so he has answered one part. Is it due to large size? It becomes very large. Antenna consists of conductors which are metals. As the size increases, its weight increases or mass increases. Mass increases means more weight. It will have an attraction towards the ground, so there will be deformation on antenna. And the larger the distance from the ground or from the earth, the uh, uh, potential energy will be larger, and that will be converted to into kinetic energy, which results in this distortion. That is why it will bend. So that is one reason why it is nearer to the ground. That is one reason. Other reason is at these frequencies, lower frequencies, the wave attenuates very fast. So you are basically these lower frequencies are aimed at short distance communication, not for large distance communication. These are aimed at short distance communication. Short distance communication, there can be blockage due to building, due to trees, etc. So line of sight communication, in the short distance communication, there will be line of sight communication. Line of sight means the transmitting antenna and the receiving antenna must see each other. So receiving transmitting antenna is in the line of sight of the receiving antenna. If they see each other, both are visible to each other. Visible means electrically visible. If they are electrically visible to each other, then the radiated field will be received by the receiving antenna. But if any obstacle is in between them, then it becomes difficult because of the obstacle, because of diffraction, etc. So in these cases, people resort to two forms of communication. One is line of sight communication, other is ground wave communication. So if the antenna is near the ground, then there will be a ground wave communication, which means like we discussed the ionospheric communication, there is something called ground wave communication. Earth crust has a conductivity, so earth will conduct it. But since it has a conductivity, it will be attenuated at a short distance. But earth will conduct it over about 20 kilometers to 25 kilometers maximum. Depending on the conductivity, there will be conduction of the signal. So line of sight and earth conduction, these two are there. Besides that, when you put the antenna above this earth or above the ground, as we discussed during our deliberations on theorems, we discussed image theory. So you have a ground, above that you have a source, then below that there will be a reflection of the source. So it will be a pair of source, one above the ground, one below the ground at the same distance. Now, if I have this antenna, if you have this antenna above the ground, nearer to ground, then below the ground there will be another antenna, and you can imagine that there is no ground but there are two antennas which are out of phase to each other because the image will be out of phase. So these two antennas are out of phase, and it forms an array. Now the array elements should be closer to each other to be directive in nature. A two element array, it is a two element array, so it will have a sign directive, sign function, sign theta function of direction. So that is how it will find out the radiation field. But if the distance is large, then this array will be ineffective. It will be like two different sources, but they will not be array, or directive property will be lost. So that is another reason for which they are placed close to the earth. I hope I answered this question as well. Uh, uh, then the next question is next question is, can we say every antenna that is grounded are lower frequency propagating antenna? The answer to this is no. Uh, the answer to this is no. All antenna are grounded. Every antenna must have a ground. Antenna will be feeding. So you feed the signal, there will be a signal part and there will be a ground part. Signal part will feed the antenna, ground part will be there for the return part. So every antenna has a ground. So it is not correct that only lower, if you are operating at lower frequency, there a ground is necessary. It is not correct that way. Every antenna must have a ground. Uh, so I hope you understand this. If you don't have a ground, there will be no return path of the for the current. So it will be an open loop. There will be no radiation from that. So every antenna must have a ground. The next doubt is how antennas are communicating with submarines. As we know that radio waves will attenuate rapidly in seawater as it is a good conducting media. Very good question. This is actually a very good question. Now, what happens in communication, submarine communication is when the submarine is nearer to the shore, which means it is around 15 to 20 kilometers from the source. In those cases, if we are if the submarine wants to communicate with the source, it will use on the electromagnetic antenna or electrical antenna. In that case, the propagation is ground wave because it is, as I told you in the previous case, that when it is close to the ground, ground waves propagate. Ground waves propagate along the ground. So the sea water will act as a propagating medium. It will propagate along the ground to the shore. So if you have there your communicating source, it will communicate with that. It will communicate with that. Otherwise, if it is not near the shore, then we do not go for EM communication. Uh, Mostly underwater communication is acoustic or sonar communication, sonic communication. Therefore, if you are on earth or out of water, we use radar. When we are within water, particularly in sea water, we use sonar, sonic communication. So therefore, we use acoustic antennas instead of electromagnetic antennas in underwater communication, and we use a hybrid of these two, electromagnetic and acoustic communication for underwater and underwater to shore communication. So this part is hybrid, this part is electromagnetic, that part is acoustic in nature. And when it is in deep sea or when it is far away from the source, 50-60 kilometers away from the source, it is only sonic communication, and in that case they do not communicate with the with the ground station directly. There are indirect ways in which sonic communication is converted to electromagnetic communication, and then you establish electromagnetic communication sort of thing. So that is a different, completely altogether different topic. But please remember that it is acoustic as well as hybrid of acoustic and electromagnetic communication when when we have submarine communication. The continuation of this question is, submarines use GPS, but GPS frequency can range over thousands of megahertz. So what is the technology for communicating the submarines? I just answered this. It is a hybrid technique, sonic and sonic or acoustic and uh, electromagnetic technique technologies. So this is the answer to Suraj whatever Suraj has asked. I think this was his last question. Then I have a question from Anvesa. Let me try to answer that. The question is the Friese formula derivation. Now, in the Friese formula, what we do or what does the Friese formula give us? It gives us, if you radiate some power, how much power will be received by the receiver. So you have a transmitting antenna, we have a receiving antenna. So from transmitting antenna is connected to a source, receiving antenna is connected to a receiver, and we want to know if we transmit some power from the source, some signal in forms of power from the source, how much power will be received by the receiver, and that power is calculated by the Friese formula. So basically what we are going to do is find out the power density. So let us find out the power density. Little रख दिया. Give me a minute, the screen has become blank. Now, you know the power density, what will be the expression for an isotropic antenna? If you have an isotropic antenna, what will be the power density? For the isotropic antenna, what will be the power density? You know, the expression for power density comes from the pointing vector S. So magnitude of pointing vector ultimately gives you the power density. For isotropic antenna, the power density S is equal to average power by R square. So U average by R square, S is equal to average energy by R square. This we have already seen and we have derived this. Now that will be equal to PT. PT is the power radiated, power at the transmitter. So PT by 4 pi R square. U average, you know, U average is PT by 4 pi. Why U average is PT by 4 pi? If total energy is U average or total power is PT, then it is averaged over the surface over the solid angle. Complete solid angle is 4 pi. So it will be PT by 4 pi. So this we have already discussed. So S is equal to PT by 4 pi R square for isotropic antenna. The moment we make this isotropic antenna directive, then how do you get it directive? In case of directive antenna, it has a preferred direction in which it radiates. So it gains some energy in that direction and reduces. So energy is directed in a particular direction. So more energy will be in a particular direction compared to energy in other direction. Therefore, we define a gain GT. So for our directive antenna with gain GT gives the how much gain is over the isotropic antenna. So from isotropic antenna, power density of isotropic antenna multiplied by the gain of the directive antenna gives the power density of the directive antenna. So therefore S is equal to GT into U average by R square. U average we have found out PT by 4 pi. So S is equal to GT into PT by 4 pi R square for directive antenna. Now in this R is the distance from the antenna in this expression. PT is the time averaged input power accepted by antenna. Wait, now what is meant by accepted by antenna? Accepted by antenna means PT stands for transmitting antenna. Transmitting antenna is connected to the source. So if the source sends power P in, out of that, after the loss in the circuit and the loss in the antenna due to conduction, dielectric, so dielectric loss, conduction, etc., loss, etc., in the antenna, after that, whatever power is the input to the antenna is PT. So that is the PT accepted by the antenna. Antenna accepts that power and radiates. So therefore it is PT is the time averaged input power accepted by the antenna. Right. Then, so this part is for the uh, transmitting part. Now let us come to the receiving part. Now at the receiving part, the antenna has a finite aperture. Everything is transmitted in a particular direction. Suppose 1 degree is the beam width. If you are at 1 kilometer direction, 1 degree will be about, you can find out how much it will be. 1 degree spread up to 1 kilometer will be uh, half a degree sine of, no, that will be, yes, sine, this will be sine or cosine, p not, tan of, tan of half a degree into 1 kilometer. 2 times tan of half a degree into 1 kilometer. So that will be very large, but that aperture, your antenna will be not that large. Receiving antenna will not be that large. It will be smaller than that. So on the aperture of the antenna will receive a smaller amount of energy, not the complete energy. The energy out of that, the total, suppose at a distance of 1 kilometer, we have about 750 meters aperture total energy. 1 degree covers 750 meters. Your antenna will be about 1 meter maximum. So 1 meter will intersect only 150 part of the uh, field of power that is coming, right? So effective aperture, if the effective aperture of the receiving antenna is AE, then the power received at the receiving antenna will be a PR. Now see the difference. Earlier it was PT, transmitting antenna, now it is PR. PR will be S, whatever is received or whatever has come from the antenna into the aperture that is receiving it. So S into A. So S into A ER. ER is effective received aperture. So S into ER, that will be S, you know, GT into PT divided by 4 pi R square, that into A ER. So at the receiver, exactly on the receiver aperture or on the receiver surface, and the power received is GT PT by 4 pi R square into AER. Now use this formula for AER, this you know. So let us use this formula. AER is equal to GR, and what is GR? GR is the gain of the receiving antenna. So AER is equal to GR into lambda square by 4 pi. That is how you find out effective aperture. So AER is equal to GR lambda square by 4 pi. Use that. If I use that, then at the receiving antenna, PR will be PT GT by 4 pi R square into lambda square by 4 pi. So that will be PT into GT into GR into lambda square divided by 2 4 pi terms are there, R square term is there. So take them together, 4 pi R whole square. So at the receiving antenna, you get PR is equal to PT into GTGR lambda square by 4 pi R square. Now, this gives us the power at the receiving antenna. And this is the common form of the Friis transmission formula. Now, I'll go slightly beyond this because I have shown you in the logarithmic formula. So take logarithm of both the sides. Take logarithm of both the sides of this common formula. So take 10 log on both sides. If I take 10 log on both sides, then and the result will be PR in dBm is equal to PT in dBm plus GR in dBm plus GR in dB, PT in dBm plus GR in dB plus GT in dB minus 20 log R, that is from kilometer, minus 20 log F in megahertz minus 32.44. This 32.44 comes from 4 pi, and F is comes from this lambda, then R remains as it is. These are in the denominator term, so you get this. Now in this, what is dBm? dBm actually is the power above 1 milliwatt. But for GT and GR, they are not power terms, therefore they are considered in terms of 1 watt. Now if the antennas are not properly aligned, what is going to happen to this formula, or what will be the difference? If they are not properly aligned, then there will be some misalignment. So because of the misalignment, there will be some misalignment loss. Similarly, if they are not in proper polarization, there will be a polarization loss. So by taking that into account, the result will be PD, received total power received, PD will be P into Q into PR, where PD is the delivered power, PD is the delivered power by the receiving antenna delivered to the circuitry or receiver, PR is the received power by the receiving antenna. P is polarization efficiency, which will be 0, which will be between 0 and 1. It is 1 if they are equally polarized in proper polarization. It is 0 if they are orthogonally polarized. It is in between these two. So these are the two extremes for polarization. Similarly, Q is the impedance mismatch factor, where Q is again between 0 and 1. If it is properly matched, then it will be 1, Q is 1. If it is not matched at all, everything goes back, then it is 0. So this is for the misalignment. So polarization and impedance, everything taken care of here. Now this will be in dB form. This will be just take log of both the sides, 10 log of both the sides. So PD in dBm will be 10 log P, 10 log P. We have found out what is 10 log P plus 10 log Q. P and Q you will be knowing, will be given to you, plus PR dBm. PR dBm formula we have just found out above. So that completes the derivation of Friis formula and explanation of what it does, why it is necessary, how you can use it. Now, if when you will go to fourth semester, there you will be reading propagation or wireless propagation, particularly wireless propagation. There you will find that in this formula there is some changes. We will add some changes to this, which is called path loss. So from point A to point B it is transmitted. So in this distance there will be scattering, because there will be these particles, fine particles will be there in the atmosphere. So there will be scattering, so there will be some loss. And there will be gases which will absorb some amount of energy. So there will be some loss. So in the path there are different mechanisms through which, because of which there will be some attenuation. So that attenuation is called path loss. So that will be again added to this formula, Friis formula. We will again take care of that path loss. So whatever you are seeing plus a path loss formula will be there. So that must the reduction by that path loss will be there. But you need not worry about that at this point. Similarly, you will find out a radar range equation when you read radar. That I have left deliberately because you have a course on radar. If you take radar, they will consider radar range equation, etc. I have kept left those things deliberately. I hope I have addressed all doubts that were there or that were raised. If you want to raise any doubt or if you have any discussions, we can discuss now. Then I will move to a shorter part of my deliberations today. Uh, I took a long part, about 1 hour on this for 40 minutes. Next will be about 30 minutes or less than 30 minutes. We will discuss about how to prepare for end-sem examination, how to put your course or course content in perspective. That we'll discuss in the next lecture. So please tell me if you have any doubts. We can discuss now, or if you want, we can wait till I complete the next lecture. Then we can discuss those doubts. So the next lecture will be on preparation for end sem. Let me take some water. Let me take a break of half a minute. Then we'll come back to this. Now, hello. हाँ अन्वेषा
Sir,
तमे क्वेश्चन करछ हाँ कुह
sir, what the materials to make a microstrip patch antenna for multi-band operation?
What are the materials for preparing a microstrip antenna for multi-band applications? Okay, what I will do is in the next class, Friday. Are you attending the next class? Are you ready for the next class? I will show you a design of microstrip antenna, how to design microstrip antenna, how to design it for example. Design example will show. So there you will know what are the materials or what you require to design a multi microstrip antenna, multi-band microstrip antenna. I have already told you how to design, but I will give you example. You require a substrate answer. Let me give you the answer today. You require a substrate, dielectric substrate. It can be a ferrimagnetic substrate or ferrite substrate also. So mostly it is a dielectric substrate. Then you have the conductor dielectric substrate which has a lower conductor at both the sides, or there are no conductors. So if you have conductors on both the sides, take one side, leave out one conductor on one side. On the other side, you etch the patch. Etch means take out. So somehow you take out a portion of this conductor on one side. That you can do in our house if you have a dielectric substrate, like suppose you have a PCB board, laminated PCB board. Laminated means conductor on both the sides, right? Take a laminated PCB board, then put some nail polish on each of the lamination. Both the sides you put nail polish. So one side completely put nail polish, on the other side put nail polish on the pattern. Right, if you are using a square patch antenna, so take a square of the same dimension on the other side, put nail polish on that part. Then take this thing, allow it to dry. So once it is dried out, take this. This is a very crude method of designing PCB. Once it is dried out, take some sulfuric acid, diluted sulfuric acid in a tray, and put this one inside the tray for some time. Now you know sulfuric acid will eat out this part, copper part. Now if there is nail polish, it will not eat out that part. So which is exposed to sulfuric acid, that part will be etched out. So that will melt in sulfuric acid. And so once that is melted, then you take it out. Now don't use your hand or gloves, putting gloves on your hand. Always put gloves when you are preparing these things. But then use forks, forceps or forks to put it in the acid and take out from the acid. That those are the precautions. So take out from the acid and put it on the below a tap, running water tap, or take some or wash it or rinse it with uh, water. If distilled water is available, it is good. Otherwise, rinse it thoroughly with water so that there is no acid left on it, right? And then remove the nail polish using any nail polish remover. Nowadays, in the market, nail polish removers are available. Remove the nail polish using any nail polish remover. Your antenna is ready. Or your PCB is ready. If you want to design a PCB, your PCB is ready, right? So that you can do anywhere in the lab. You can do it in your house. You can do it. It will cost you around at best 500 rupees, not more than 500 rupees. Within 500 rupees, you will be able to get everything for 5 to 10 antennas. You can design 5 to 10 antennas using this. But the calculation and design, that I can give you an example. From the example, you will understand how you can do this, how you can draw the pattern. Okay. I hope I answered this part.
Yes.
So now let us come to your courses of studies, excluding the ionospheric part. Today I will consider only the antenna part, and ionospheric part you can automatically prepare once you know this. Now in the antenna part you have section 1, section 2 and section 3. Ionosphere is section 4. Now and let us concentrate first on section 1. In section 1, you have antenna characteristics. Now in the antenna characteristics, important part is, for me, important part is antenna pattern. Now in the antenna pattern, that you subdivide into groups. So I have subdivided it into groups: power patterns and field patterns. Now what is the difference between these two? What is the difference between power pattern and field pattern? What is the definition of power pattern and field pattern? What are the explanation and between power pattern and field pattern? These are three questions that can be asked on each of these points that I have showed. Uh, when there is a and, which means you can find out what is compare and contrast. Question can be compare and contrast between power pattern, field pattern, or compare power pattern and field pattern. Then the question can be define power pattern, define field pattern, and explain what you mean by power pattern, explain what you mean by field patterns. These are the questions on the first part. Mostly these will be coming in your section A. You have three sections, as you know, in your end you can have three sections: section A, section B, section C. So these are the questions that will come in the section A. Define and explain. This will be mostly in section A. Compare and contrast, that can be in section B. Now now let me try to answer this one only. Others you can do yourself. Power pattern and field pattern. What is the difference between power pattern and field pattern? Power pattern is the square of the absolute field pattern. So take E. Only if I am going to draw E, then that is field pattern. If I am going to draw absolute E square, that is power pattern. Now in the field pattern, it will have positive and negative, both values can be there. In the power pattern, it will have only positive values. The reason is it is a square. Square is always a positive. Square is always positive. Other numbers may not be positive, but square is always positive. So field pattern and power pattern, if you draw field pattern, above the zero line there will be some portion of the pattern, below the zero line there will be some portion of the pattern. The below the some zero line, the portion of the pattern which are below the zero line, they will be flipped. So to explain this, you have to draw the figure in the Cartesian coordinate system, not the polar plot, the Cartesian coordinate system. So for power pattern, there will be a peak, then there will be a dip, then there will be a peak, then there will be a dip. So that will be the power pattern. Field pattern, everything will, there will be a peak, then there will be a smaller peak, then there will be a smaller peak. Main beam is a peak, side beams will be smaller peaks on each side. So that is how you will explain. Now what is the use of these two things? If you take field pattern and average it, it will be a small quantity. But if you take power pattern and average it, it will be actually its average, positive average. What is the difference between these two? Small quantity, it is difficult to measure. Always we are interested in time averaged part. So when you go for a time averaging, the field pattern gives you a very small quantity. Power pattern gives you the proper value. That is why power pattern is more useful. Basically, what you are measuring is not the field, you are measuring the power. You cannot measure the field. I have a lecture on 29th evening, sorry, 19th evening, 8 o'clock uh, for a conference. Uh, I wish you attend, all of you. Those who are interested in antenna, please attend that lecture. What I am saying, you will understand there completely. Basically, you will understand your antenna, and if you are interested in doing research at some time, fundamental research, that also you'll get a hints on that, on the, or what are the fields which are open, basic fields, that will understand there in that lecture. So this is what is about the compare and contrast. Then power pattern, um, by definition, power pattern, you can define what is the power pattern: the variation of power over space in terms of theta and phi. That is power pattern. Similarly, field pattern is variation of power over space in terms of theta and phi. That is field pattern. By these are definitions. Other definitions I have given you in the class. These are the two definitions. So if definition is asked, only write this, don't explain. If explanation is asked, then you explain that phi power is required because it is the measurable quantity, so power pattern is required, whereas field is not directly measurable, right? So since field is not directly measurable, power is directly measurable, so we measure power. So that is why power pattern is more important. And the variation of power over the space is gives you the power pattern. So that explanation you have to give. So at some places power will be more, some places power will be less, unless it is isotropic. If it is isotropic, it will be, power will be same everywhere. Otherwise, it will be more in the preferred direction, it will be less in other directions. So that explanation you give for power pattern or for field pattern also. In the explanation, this part is to be written. Definition only define, don't go for explanation. Compare and contrast, you compare and contrast the way I say. Similarly, what is reactive field, what is radiation field? Similar questions will become. Then you can have questions on the field regions: reactive near field, radiating near field, and far field. Field regions you can divide into three categories: reactive near field, radiating near field, and far field. So what are the definitions? Comparing them. What is the difference between reactive near field and radiating near field? What is the difference between radiating near field and far field? And so those things are there. Then definition of different patterns. Different patterns means isotropic pattern. What is the isotropic? Different types of pattern. One is isotropic pattern, one is directional pattern, one is omnidirectional pattern, one is principal plane patterns. All these we have given you the definitions. So these definitions are important. So go for these definitions. So get ready with these definitions for your section A. Then on the parameters of the pattern: main lobe, major lobe, minor lobe, side lobe, back lobe, then half power beam width, first null beam width. So these are the parameters. You can divide your course accordingly and get prepared. And then antenna average power, that comes from the Poynting vector in antenna. So these are in terms of antenna pattern. Then antenna performance parameter. Next is antenna performance parameter. In the performance, you have found out what is the radiation intensity, the directivity and beam salad angle, then numerical evaluation of directivity. This will be a question in section B. Numerical evaluation can be a question in section B. Antenna, again, all these can be questions on section B or definitions in section A. Antenna, again, all these you can have some simple numerical problems in section B. Then antenna impedance. Under antenna impedance, you will have to say what is loss resistance, what is radiation resistance, or what is reactance, associated power components with reactance. Then what is maximum power transferred to the antenna from the antenna to the space. Impedance matching, what you mean by impedance matching, what you mean by transmitting and receiving systems in terms of antenna impedance. So then some knowledge on transmission line, because that determines what will be the reactive part of the antenna, what is be the unradiative part of the or R part, resistive part of the antenna, which includes radiation part. So that is why transmission line is important. So the fundamentals of that, just brush up the transmission line, particularly ZIN, formula for ZIN, that part is important. And then polarization, three types of polarization: linear, circular, elliptical polarization. Then what is effective aperture? I have just discussed it. I revised this today. Depending on scattering area, loss area, and capture area. So this part you can prepare from Balanis. And then antenna system performance, in which the phase transmission equation is included. So this complete thing is for your um, unit 1, first unit of the course. Then we will come to the second unit of the course. It is simple. A second unit has two parts. One is wire antenna, one is the antenna radiation field using potential. These are the two parts. I divide it into these two parts. In this part, determination of antenna radiation field using potentials, you start with Maxwell's equation. So try to remember Maxwell's equation both in time domain and in frequency domain. Frequency domain means Maxwell's equations for time harmonic field. Time harmonic field is always a monochromatic field. Remember that. It is always a monochromatic field. Monochromatic means there is only one frequency, not more than one frequency. You do the analysis for one frequency, then you can use Fourier analysis or Fourier transform, etc., Fourier series to find out the frequency over a broadband of frequency, or the performance over a broadband of frequencies. And therefore Maxwell's equation is important. Then from the Maxwell's equation, go to what is potential, how you define potential, Gauss transformation, etc., everything. Vector potential, scalar potential, Gauss transformation. Then come to the far field approximation. So then, then come to the far field approximation. So important part is Maxwell's equation, then far field approximation, then use of coordinate system, particularly spherical coordinate system, to find out the far field, then duality. And duality is the duality of electric and magnetic fields. Particularly this is important for the aperture antenna. So I have put it here because I have not taken that as a separate entity in the consideration. I have put it here because these are the principles that you are using there in the aperture antenna, the theorem. So everything comes under duality. That I have not put in a separate manner. That comes here. So this is one part. Then comes your particular antennas like wire antenna. So that again has four parts, four important parts. One is infinitesimal dipole, then application of Poynting theorem to that. Then you go to short dipole, then we have center field dipole. In this, what you have to do is first go for infinitesimal dipole, find out what is near field, radiating near field, far field, far field of an arbitrarily oriented infinitesimal dipole. What we have discussed is far field of an infinitesimal dipole oriented along z axis. So it can be arbitrarily oriented. So along x axis, along y axis, or along any other axis. So find out that. That can be a long question. Performance parameters. What are the performance parameters? Radiation resistance, directivity, beam solid angle, and effective aperture for an infinitesimal dipole. These are the 1, 2, 3, 4. Or these are the four performance parameters which are important from examination point of view. Then go to Poynting theorem. Poynting theorem actually you will be using in finding out the beam solid angle that will require then power radiated. Those things will be required. So that is why you will use Poynting theorem. We have already used that. And then extend that to short dipole. For the short dipole, again you find out the fields that we have discussed for the infinitesimal dipole, same fields. Then performance parameters, same performance parameters. Then go to the center field dipole, under which comes the half wave dipole. So in this, again, fields, performance parameters, input impedance, and particular stress is to be given on half wave dipole. So this is about wire antennas. Same thing is applicable for microstrip antenna and horn antenna. In the horn antenna, only thing is you have to remember that it is an aperture antenna. The field over the aperture is same as that from a feeding waveguide, and from the field using equivalence principle you can find out using equivalence principle you can find out the current, from which you can find out the far field. So only far field is important in for horn antenna. Other parts you can neglect. I hope I wish we can have some time for this horn antenna discussion on horn antenna results. So we'll discuss that later if I find some time later. Then microstrip antenna. Microstrip antenna. Before microstrip antenna, arrays. Again in arrays, try to understand what is two element array. That can be a question in section B. Then pattern multiplication, it can be in section B or section C, both cases. Then what is array factor, what is element factor, so those things. Then the types of arrays, uniform array types, broadside array, end fire array. Then Hansen-Woodward end fire array, that is, this part is important. These 1, 2, 3, 4, these four are important for you. The fifth you can neglect, or if you are ready to take it, take it. Non-uniformly excited arrays, particularly the binomial array. Other parts you can neglect from your examination point of view. And some examination point of view, we can neglect other parts. Then, so this is for preparation of your NSEM examination. Similarly, you can consider the ionosphere. In the ionosphere, part 1 is formation of ionosphere, behavior of ionosphere, layers in the ionosphere, then duality constant of the ionosphere. So this is one part. Other part will be maximum usable frequency, secant law, virtual height, and then skip distance. These will form second part for a question, full question, or they can be in parts in section A or section B. Then the third part will be a full question only in the section C, which is effect of Earth's magnetic field. I have shown you the effect when the field is oriented along the z-axis. So B is equal to g cap z0. B is equal to g cap z0. Now you can take B is equal to uh, g cap sorry, B is equal to x cap plus y cap into B0.